And our next speaker will be Christian Hummel, who will tell us all about using VLTI.
Yes, of course. So with this title, I would like to promote more the use of the VLTI, because you might think that this is a difficult technique and instrument to use, or telescope to use. But it's easier than you think if you have already used other telescopes from ESO before. And the reason for this is that over the years, VLTI has been very successfully integrated in the entire science operations scheme, and also here on our side, that basically we have the same phase 1 proposal process for the VLTI, and we have the same phase 2 process, service mode and visitor mode. One thing I would like to point out here is that we have had a lot of help from the French community via the JMMC. This is the Jean-Marie Mariotti Center in Grenoble. They have provided tools which help you with planning observations, and they even provide pipelines, for example, for Pioneer. And whereas the pipelines for other instruments are, as always, are available on the ESO web pages. So let's start with the project you might have thought about, and what is really unique with the VLTI is you can actually choose your telescope size. So how about that? If you want to have a 130-meter telescope, then fine, we have it. It's the array of the 4 UTs, for example, has baselines up to 140 meters. With the 80s, you can reconfigure your array. Here you can see, for example, you can have an array with a 1.8 meter telescope, which simulates a 90-meter telescope, or you can have even smaller ones on the order of 20, 30, or 40 meters. So if you thought about a project like imaging a star, which is something which has already been done several times now, it's sort of the latest and greatest endeavors we can do in interferometry is to image stellar surfaces. So there's this AGB star Pi1 GUI, which I'm going to use as an example. And this is an Herschel image showing a big blob with a size of about 1 arc second in the far infrared. So for this star, we choose a telescope, and now here is something where I need to add a little bit of theory. The size of the telescope you choose depends on the size of the target. So this target here is on the order of 20 milliarc seconds. And when you observe this with an interferometer, we observe the fringe contrast, or the contrast of the interferogram, which is created when you interfere the lights between the telescopes. And this contrast is normalized to 1 for 0 length baselines, and then it drops pretty quickly. And we call this, when we see this visibility drop, we call this the target is resolved. This is just as a term we use. It basically means we start seeing detail. We see how big the star is, for example, just by looking at what baseline and at what wavelength the visibility contrast has dropped to 0. And then it has these little bumps here, which are magnified here on the right. And these are the so-called nulls, where the visibility goes almost to 0 and then it bumps up again. And you see the contrast is very low here. It's like only like 0.1%, for example. So this is quite a challenge to observe. But this is where all the information is, where you see where you start seeing the limb darkening, where you can see this, where you can deduce information about spots, for example, asymmetries, all sorts of things happening on the stellar surface. Okay. So you need to have an idea of the size of the target before you choose the size of your telescope. And this is also where ASPRO, this is one of the tools offered by the JMMC, allows you to enter, for example, here in a mask on the left, some information about the object, how big it is, and so on. You choose an instrument and a wave configuration, and maybe even the wavelength setting if the instrument has several settings. And then you get a great plot here, which shows you these nulls. Maybe you can see them. These are these circular dark lines, and it overplots the aperture coverage you get with the configuration you have, because in the difframeter we don't have a filled aperture. So there will be measurements at all these blue crosses here and the red crosses, and it tells you, gives you a very good idea of whether this configuration is good or not good for your object. Yeah. So then, after you chose your telescope size, then you are in the middle of phase one, and so you start writing a proposal. You have your title. We would like to image the surface of a star. One particular technical remark is that you ask for runs per configuration instrument. So I have an example here of one single one, which is A, because this was a program I submitted, which just uses the 4 UTs, and you cannot move them, obviously. But with the ATs, you would have different run letters for different configurations. Then, very important, please check the instrument web pages for your instrument about limits. Is the target bright enough, or is it too faint? With the UTs and gravity, we can go to magnitude 10 now, which is very interesting compared to a few years ago, where we only could go to like 4 or 5 or 6. And so you have to fill one additional box here in box 14, which is a box which is specifically for interferometric targets. You have to choose the configuration, and you have to add a little bit of information about what kind of visibility amplitudes you expect. Yeah. If the target is very resolved, then you have to compute the correlated magnitude, which is very simple. You just take the visibility, take the logarithm of it, add it to the multiply by minus 0.25, and add it to the apparent magnitude of the star. And then you get the correlated magnitude. And this you have to compare to the limits allowed for this instrument. Okay. So there's another particular thing which is also maybe history in the not too distant future. When you choose an array, we have all this information on the Paranal telescope pages. You just go to Paranal and go to VLTI configurations. And then you see a little scheme of the configuration which is offered. There are 3 configurations which are offered with plus the UTs. But because if you don't use the UTs, use the ATs, the 1.8 meter telescopes, these are little small telescopes, and some of them sit really awfully close to one of the big ones. And so if they look, they can't look over the big dome next to them. This is what produces these big shadows. For example, here's a big shadow, which is UT4. You see that one, that's stationed pretty close to UT4. And so you have to put into the OB these LST constraints, local sidereal time. This is a parameter which is also available for other instruments, telescopes, for various reasons. But here we use this LST constraint to make sure that the OB is not started when the target is actually in the shadow of one of these big telescopes. In the future, this might disappear because the scheduler right now is a little bit challenged to do all these computations for all the hundreds and thousands of OBs in the queue. So we do it before offline, and so the scheduler doesn't need to do this computation again. But in principle, it could do it, and we're working on this a little bit. So calibrators have to be selected. These are stars with small angular diameters. So if the angular diameter is small, the visibility should be 1, but in reality it's never 1 because of the atmosphere and instrumental effects which decrease the contrast. But so that's why you observe the calibrator, and you just take the science visibility divided by what the calibrator was measured, what the visibility of the calibrator was, and that is it. That's the calibration. So it's really, really easy actually. And then you have a calibrated data set you can work with. And again, JMMC offers a tool called SearchCal, and also on the ESO VLTI pages, there's a Kelvin tool where you enter the target coordinates, and then it suggests a list of calibrators to choose from. And those you actually put on those concatenations Giacomo mentioned. So we have a concatenation. This is ideal because for every science target, we need a calibrator. So you put those in the concatenation. So you make sure that every science object is paired with a calibrator, yeah, and is never forgotten. So then we have check. Yeah. So this is a plot showing the UV coverage, which came out of this project of P1 GRU, which is actually an object which was published recently in Nature. And these are the this is the coverage, basically the aperture coverage, your telescope, and where the measurements were taken. So the telescope aperture is this, basically, but of course it's not filled, and you have measurements at all these various points. Okay, and two configurations, red and blue, were used for this. So the observations were completed. You know, we had the phase 1. The phase 2 was submitted. You submitted the Bs. The observations are completed now, and now you can. For this example, these were observations done with Pioneer, and you run the Pioneer pipeline, which was written by Jean-Baptiste Le Bouquin, which is really amazingly simple. You just download the code, compile it. You go in the directory where the raw files is. You type in pndrs reduce, and it reduces the entire data set. Then you type pndrs calibrate, it calibrates it, and you're done. So it's really, it could not be easier. And the output is stored in a so-called OI fits file. It's basically fits with binary extensions. This is an example of what it looks like. And there are tools to read this format. And if you really want to look at individual items. So I have a few slides added here, which I took from various talks with colleagues of mine have presented those before, and they're going to be online, so I'm not going to mention everything. These are tools to read these files, these OI fits files, and Python tools to reduce gravity data, for example, unless you will use reflex. So I'll just leave those in the slides to be online later on. There are tools for visualization. For example, there's the OI Fits Explorer from JMMC. You just go to these links. You could even use FitsView to extract tables. And there's a quick look tool written in Python by Antoine Meron, which you can download from GitHub to look at gravity data in a very quick way. There are lots of modeling tools. JMMC offers LitPro, where you can fit a stellar disk, a binary model, or more complicated models. There's MFIT. There's even in the US, the Nexi Center offers tools. I'm offering a tool. There's a candidate companion detection tool if you're doing surveys for companions of stars. So image reconstruction, we're getting closer to the grand finale. There is actually almost an explosion of image reconstruction softwares, because image reconstruction, the optical interferometry data, is really quite a challenge still. But some of these tools, for example, Irbis, they're quite far evolved. This is offered with Gravity. Yeah, Squeeze is also a quite important algorithm. So, and this is actually, these are images done, I forgot whether they use, I think they use Squeeze for this. And so this was actually published by Claudio Palladini a couple of months ago in Nature. And you see this 20 milliarcsecond disk with these huge spots on the surface, typical for an AGB star. So this is something you need a telescope with a diameter of like 60 meters or so. And this is my last slide. This is another page. There's a European VLTI expertise network, EII. You can go to this link. And what this also has in it is information about upcoming interferometry schools. There's one coming up in Porto this year, and I think it will have information on it. You can go there, and there are lots of tutorials and experts, and I think it's like 1 or 2 weeks long. So if there's anything you ever wanted to know about interferometry, this is the best way to proceed. Thank you very much.
Thank you, Christian, for a very nicely delivered talk and on time. Questions for Christian? If not, do we have any of our participants online that have any questions for Christian? If not, let's thank Christian again.